Okay, so thank you everyone for being here. I'm so excited to present this work, ScopeVerif. So let's get started. Sorry, okay. Yeah. So basically on Android, there are two ways for apps to save a file. It's either on internal storage or on external storage. Internal storage are like private storage where apps only have access to their own files, but other apps should not have access to our files. And on external storage is more like a shared storage. Prior to Android 10, the file access control permission design is pretty coarse-grained. So once an app with permission granted by the user, it automatically has access to everything on the external storage. Also, if an app can request user interaction, then if the user approves, then the app will also have access to everything on external storage. The best analogy I can think of is like a mailroom situation. So like if you go to a mailroom to pick up your own packages, once you have access to the room, not only you can pick up your own packages, but theoretically, you can pick up other guys' packages. And since Android 10, there's a huge redesign on file access control model. So it's called Scope Storage now. And basically, it converts the mailroom situation into a locker room situation where now apps should only have access to their own private folders and not other apps' folders. So if you look at this diagram, for app-specific folders, which are private folders, now you can see that only the owner app should have access to these private folders. And other apps, even with user interaction, even with permissions granted by the user, they should not have access to the private folders. However, Android storage is really complex, and its implementation on storage varies among different implementations. So sometimes, inevitably, it creates unhandled corner cases which may result in security and privacy issues. One well-known issue is what we call SAF loophole. So basically, it's a loophole that allows attackers to partially bypass scope storage and leads to unauthorized access to files stored in other apps' private folders. While this issue might seem like a very minor, specific issue, but in fact, the root cause, the underlying issue for this is actually much bigger. Because as we see, the scope storage is not only one rule, security rule, it's a list of rules. And the issue we mentioned earlier is just violating one of them. But how can we ensure if scope storage is implementing every rule correctly? And this actually motivates us to think about more in general. So how correct is scope storage? And how consistent is the implementation between different versions and devices? And how effective is scope storage in preventing security or privacy issues? So to answer these questions, there are multiple technical challenges. The challenge number one is there are multiple API for file operations. Some API might be able to run in background, and some might require user interaction. And these different API will have different expected behaviors. And it is challenging to have a comprehensive solution to cover all these different expected behaviors or exceptions. The challenge number two is we have a large and fragmented code base. So ideally, we really want to see a single component having all those scope storage checks being implemented in a very centralized manner. But in fact, the logics are being implemented among different components and even in different layers. And sometimes there will be duplicate logics implementing one component which is implemented correctly, but in another component is implement again, and there's some problems there. So this is the challenge number two. And challenge number three is that, as we know, we have lots of Android versions because Android is iterating very quick. We have 12, 13, 14, and with each update, there will be some changes in the implementation of storage access control model. And sometimes these changes are very subtle and even undocumented. Also, other than this, we know that Android can be run on different devices, and different vendors may have their own customized version of Android. So Based on this situation, we know that verifying a single combination of them is definitely inadequate, and we would like to have some comprehensive solution that can also be future-proof. So this leads to our approach. In general, the idea is we adopt dynamic analysis. And the procedure is pretty straightforward. We come from documentation, we extract security rules from documentation, and for each security rule, we generate multiple test cases. And then we run these test cases and to determine if there's a violation to security rules or not. In more details, if we look at this, we have a natural language security rules, and we want to translate it into a security rules. So the key step here is to determine the type of the rule. So it's whether a confidentiality, integrity, or availability. So in this case, the security rule is a confidentiality because we are saying apps do not have access to other apps' private files. So this is a confidentiality rule. And then for this security rule, we want to generate multiple test cases. And if we look at the attribute actions here, this means for this security, so this means this security rule applies regardless of whether you're reading a file, write a file, move a file, or rename a file. This confidentiality should always hold. And in this case, read action itself becomes one of the test cases. Then, how do we determine if there's a violation or not? The general idea is we use differential analysis. Basically, we want to construct a baseline first, and this baseline means what do we expect to see if the property holds? And then we compare it with the actual execution results. For example, for confidentiality, how do we construct baseline? So basically, let's imagine what could be the perfect secrecy for file access. In order to, when we access a file, the perfect secrecy is we don't even know whether the file exists or not. So based on this intuition, we design ScopeVerif to first ask the test app to read a file path that there doesn't even have a file there, so there's no file there. And we collected the feedback as the baseline, and then we execute our test case, and then we compare them. So if there's any difference, that indicates at least the existence of that file has been leaked. For integrity, it's similar. So we basically construct the baseline before any modification attempt by reading the file first time. And then we run our test case. We try to delete the file. We try to override the file. We do a lot of things. And then we read it again to collect the actual test case results. And we compare them. If there's any difference, that means the integrity of the file has been violated. For availability, how can we know if a file operation is being available to our testing app? Well, we ask the root user to do the same thing, and we collect the feedback. And if they are the same, that indicates at least the testing app had the same capability as the root user, which means the file operation is being available to the testing app. In summary, ScopeVerif found 10 issues. 9 of them were previously unknown. And they also revealed inconsistent implementations across different Android versions and OEMs. Also, ScopeVerif can automatically identify previous unknown issue within a day. So I really want to share this case study with you. It's what we call metadata leak. So basically, ScopeVerif found if you use File API to read a file in another app's private folders, if the file exists, it will say permission denied. If the file doesn't exist, the exception message will show no such file or directory. And using this message, we will be able to tell the existence of another file stored in other apps' private folders. And note, to perform this attack, no permission is needed. And this actually will lead to privacy concerns because it enables attackers to perform persistent cross-app user identification. The exact detail on performing this attack is explained in our paper, so I strongly encourage you to read our paper to learn more about this. Another case study is what we call the SAF loophole, the Huawei version. So basically, we found that the ScopeVerif found that on Huawei's Android 14 builds, if you use this API in a specific way, it allows attacker to create or overwrite files in another app's private directories. So, and the interesting thing is, the ScopeVerif also found this issue in earlier version of Google's Android. But Google later, they released a patch to fix this bug. But for some unknown reasons, Huawei did not adopt these patches. In summary, we did a systematic automated analysis of Android's permission model regarding file access, which leads to ScopeVerif. ScopeVerif utilized differential analysis to verify the correctness of scope storage implementation, as well as identify inconsistencies between Android versions and devices. ScopeVerif also found previously unknown issues, including security and privacy issues. We reported all of our findings to both Google and Huawei, and both companies offered us bug bounties. Thank you.
Let's thank our speaker. Okay, Q&A. Any questions? Fantastic. Introduce yourself. Go ahead.
Yuxin Yang from the Ohio State University. So very wonderful talk and learned a lot for the research. But I was curious, you know that the Harmony OS, the Android is very fragmentation. Harmony OS is hardly very heavily customized. Do you think that this sort of research can be applied to the deeply customized operating system, and what kind of vulnerability you can foresee? Will that be a little bit more, devastating, or something new can be achieved through that?
So, are you asking how likely can we adopt our tool on Harmony system?
Yeah, like because they are separated in two different ways, there can be a lot of inconsistencies. And what kind of problem would you like to foresee? Do you think that it's feasible for us to explore more into this Harmony OS and like the Android? I was wondering.
Yeah. So, in our research, in our studies, so basically the observation is that we found, based on the results, we see. So, other than the SAF loophole Huawei version we discussed in the presentation, everything else are the same. So it's like whatever happens in other Android, Google's Android, it also happens on the Harmony OS. So that's our observation.
Yeah, I think that's very promising. Thank you so much.
Yeah, thank you.
Okay, excellent. Anything else? Oh, one more. Go ahead. Probably the last one.
Hi, thanks for the talk. I'm Wei-Tong Chen from Microsoft Research. I have one question. Do you have observed any false positives?
So you're asking, so do we met any false positives?
Inconsistency that doesn't recognize as a bug?
So I wouldn't call them false positive because the way we did it using this differential analysis, so assuming the environment is controlled pretty in a nice way, then we don't have too much true false positive because they're really actually violating the security rules. But in fact, we do found there's some violations that they're not really bugs. For example, there could be some undocumented features or undocumented exceptions for some certain API usage. And after we communicate with developers, we know that this is intended behaviors. So this might be one of your... Yeah.
Thanks.
Yeah, thank you.
All right, this just in. You're on the job market, I hear. Excellent, excellent. So if you like what you've seen, give them a call. Hire.
Thank you very much.
Fantastic. Very good work. Let's thank all of our speakers one more time.